talk of Malliavin from Odessa University, with title of the talk, Lyapunov exponents for the system of stochastic differential equations with interaction. Please, Maria.
Good evening. Thank you for the honor to make a talk for the seminar. And now I turn out my video because I have not very good internet. My talk, Lyapunov exponents for the system of stochastic differential equation with interaction. In 19th century, I.M. Lyapunov proposed two methods for studying the systems of ordinary differential equations, which deals with the long-term behavior of solutions. It was the method of characteristic numbers, which now bear his name, Lyapunov exponents, and the method of Lyapunov functions. Since then, the methods of Lyapunov have been widely used and serve as key tools in the theory of differential equation and related fields. Consider the dynamical system 1, and it is defined in an n-dimensional space where f is a continuously differentiable vector function. Then the time evaluation of the tangent vector delta x at x from t is represented by linearizing equation 2, and here f big is the Jacobian matrix of f with respect to trajectory under consideration. And the spectrum of Lyapunov exponents is given by the formula 3. In the paper of Osledis, it can be used the multiplicative ergodic theorem, and we can claim that this all limits for all the trajectories are finite. For a linear system of differential equations in RD, Lyapunov proved that the collection of all Lyapunov exponents to all of its solutions consists of at most d distinct finite numbers, if it is in RD. In here, for the d-dimensional dynamical system, there are d Lyapunov exponents in the spectrum of attractor. In general, for dynamical system, we have four cases, and three of them are the next one. The first is fixed point if all Lyapunov exponents are negative. The second one is the limit cycle if the top Lyapunov exponent is equal to 0 and the other are negative. And torus if the top Lyapunov exponent and the next one are zeros and the other are negative. And these cases are considered exactly in the next paper of Ekman and Ruel. In 1985, Carver-Hill defines the Lyapunov spectrum and filtration for a stochastic flow of diffeomorphisms on a smooth compact Riemannian manifold M of dimension M small. Let M big is a smooth compact M-dimensional Riemannian manifold. V0, V1, and so on are smooth vector fields on M, and WT1 and so on are independent one-dimensional Brownian motions. In 1986, Baxendale proved the next theorem that the limit 5 exists on the set of the probability 1, and the eigenvalues of this limit matrix C from X omega he called the Lyapunov spectrum of stochastic flow, and the exact values from fixed x and omega and lambda omega x, he called the Lyapunov exponents of such a flow. For the case of isotropic stochastic flows, Lyapunov exponents can be calculated exactly. A stochastic flow psi t of diffeomorphism of Rm is said to be isotropic if for all rigid motions g of Rm, the flows g psi t j minus 1 and psi t have the same distribution. For an isotropic stochastic flow on Rm and a fixed x from Rm, the derivative d psi t may be written as a product of independent, identically distributed random matrices. The isotropic stochastic flow is characterized by its covariation, and in the same paper of Baxendale, it was proved that in this isotropic case, this Lyapunov exponent can be written by the formula 6, and here beta L and beta N are non-negative constants depending on covariation. My point was to use this Lyapunov methods and Lyapunov exponents to consider the asymptotic behavior for stochastic differential equations with interaction. And let us consider the general form of such equation. And here our stochastic equation depends on the another points that are in our stochastic flow. And here is the definition of solution of stochastic differential equation with interaction. My point was to consider the equation 9 or 8, and that is the next one. To consider to deal with such an equation, there are some conditions on the functions phi and b. They are in some sense similar to the conditions that was considered in the book of Andrei Anatolyevich Drogovtsev, but there was one-sided conditions, and for such an equation here there are two-sided conditions of our right part. And here we have the relation of these constants alpha and b, that is 12. To investigate the asymptotic behavior of solution of such equations using Ito formula, we get the formula 13 with the next subsidiary notations. And before it was proved that there exists the next limit almost everywhere. So this is a right, if we put here the integral of phi big into the left part, so we have that it will get a limit on infinity almost everywhere.
Masha, can I ask you the idea of the proof of the theorem, why this limit exists?
We see that if we put this integral into the left part, so we use the properties of our stochastic integrals, and we have that it will be the Wiener process of the quadratic variation of the sum of pk square. And then it was proved in other papers that it has a limit on infinity, and that's why it exists.
Thank you.
But now my point was to use Lyapunov exponents and to calculate it precisely. I considered at first the system 15. It is the linear case of equation 8, and this such a form of these matrices, so these are only 3 parameters, is because of these conditions. So this equation have to satisfy all these conditions, and therefore we can get only 3 parameters and only such a form. And we have that q is here negative, and it is less or equal minus 2p squared. Let us now suppose that q12 is not equal to 0. And then I tried to calculate the Lyapunov exponent, and I get a system for my partial derivatives x from ut, and I get such a form. So if we consider this system, we understand that we don't have to consider the system of the fourth order, and it is enough to consider the system of the second former. Wait, it's okay. Of the second order of the form 17.
Masha, again, excuse me, can you go back for this? Can we say now that there are no any influence of interaction? So it does not depend on the initial measure, yes?
Yes, because if we calculate this derivative, so we have we can rewrite these integrals because x
so
from
this
ut
is due to linearity of interaction.
Yes, yeah? yes. And
this
therefore,
is not only linear equation with respect to the argument, but it is linear also in the sense of interaction between the different particles. Okay.
Yes, and therefore it doesn't depend on the interaction, and we also can consider the system of 2 equations of the type 17. And then I found the paper of An and Hai, and they calculated the top Lyapunov exponents exactly for the systems of the second order. And I used the result for the system 17. And I get that it has the next form, where Q, P are from my system. And now let us notice and let us prove that for my case, so if Q12 is not equal to 0, P is greater than 0, and Q is negative, always this top Lyapunov exponent is negative. Let us see why. Exponent in this, let us see the first part. Exponent in some power, it is positive. Q is negative, therefore minus Q is also positive. So the first, this one is positive. Then if Q12 is negative, then exponent in the power 2 q1 2 pi divided by p squared is I said, if Q12 is negative, then exponent in such a power, it is exponent in the negative power, and it is less than 1. So the third, our expression is positive. So all that is negative, and Q is also negative, and so the sum is negative in this case. If Q12 is positive, then the second one, 1 minus exponent in the positive power is negative. So we also have that all this third addends is negative, and plus Q is also negative. We have that it is also negative. So in all our cases, the top Lyapunov exponent is negative. And what do we do now? Then I considered the difference between my x from ut minus the center of the mass. The center of the mass is the next integral. And what do we get? Then we get that this difference satisfies the same linear equation 17 that doesn't depend of our interaction. So we get just a linear stochastic differential equation with constant coefficients and this one. And we get the next the same differential equation that we had just calculated the Lyapunov exponent, and we now proved that this the top Lyapunov exponent is negative. And then we have that we know what is this, that stochastic differential equation is exponentially stable, that the next limb sup is negative almost surely. So if we in our case have that our top Lyapunov exponent is negative, so we have that our SDE 17 is exponentially stable. And looking what was this system, we understand that our solutions exponentially tends to the limit of our mass, and the behavior of different particles are the same on infinity like the behavior of our center of the mass. And now we understand that this is in some sense related to the shift compactness that was investigated in the works of Andrei Anatolyevich Dorogovtsev. So in the paper of Andrei Anatolyevich Dorogovtsev and Maria Karlikova, it was defined what is a shift compactness, and we call the set of measures to be shift compact if the set of measures mu alpha minus u alpha is compact. And also for differential equations with interaction, there was considered the next example that also shows that not always the solutions of stochastic differential equation with interaction have to have the Lyapunov exponent that are negative, because we here have that the x from ut minus x from 0t has a limit, so it can't be that the top exponent, Lyapunov exponent, is negative. So it is in such a sense also an interesting example. And it was proved in the papers of Andrei Anatolyevich Dorogovtsev and Maria Karlikova that the condition if the set of measures of our differential equation with interaction is a shift compact. And if we look of condition 22, it is in some sense similar to conditions in my SDE, but it is one-sided. And also there are the condition on the numbers alpha and so on. And it can be made some relativity with Lyapunov exponents and shift compactness. And now my point now is to try to use these Lyapunov methods to general case, not only for the linear case, and to try to get some results and to understand does the limit behavior of solutions in general case also is the same, that we have that all solutions behave on infinity like the center of our math. And this is my point for today, and thank you very much for your attention.
Okay, Masha, thank you very much for your communication. What I must to say is that maybe you have some bad habit, because your previous talk also was 20 minutes. We have talk like 1 hour. So you have to prepare next talk for 1 hour.
Okay, thank you.
But nevertheless, maybe somebody have questions or comments, please. Okay, it is interesting to see what happened with the full spectrum of the Lyapunov exponents in the case of equation with interaction. Because it is for usual equation with no interaction, it produces for us not only values of Lyapunov exponents, but some subspaces of the initial space, where we have repelling or attraction relatively to the sign of Lyapunov exponent. But here we have seen already, even in the simple linear case which you shows us, that it can happen that everything follows to the center of the mass, for example, of the measure. But what happened if we have one negative, another one positive Lyapunov exponent? What happened? So it can be interesting, and maybe we can expect some new effects related to the interaction. So let's see you next talk, but 1 hour talk, okay?
Okay, I will try.
Or you
okay.
You can make 3 talks, 3 20-minute talks.
Okay.
Okay, if there are no any other comments or questions, then we will end our session. And Georgi, do you know who will be next speaker?
Andrei Pilipenko will talk about QLV process.
Very good. Today we finish early our work. Thank everybody, and bye for the next week. Bye.
Thank you.
Bye.
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 Bye.